Let's have a look at total surface area today under the umbrella topic of surface area and volume. Now, total surface area, ladies and gentlemen, refers to the total area of every surface on the outside of any three-dimensional object. Now, let's have a look at rectangular, prisms and cubes firstly, okay? Then we're going to look at spheres and cylinders and cones. My goodness, it's very interesting. Now, first of all, we're going to look at this thing here. It's called a rectangular prism, and the reason it's called a prism is because if you were basically to get a knife and chop this down this away, right along, say, this width here, you get the same cross-sectional area, like slicing a loaf of bread. You get that shape. That means it's called a prism. That's just a little bit of incidental information. Now, for the surfaces of that object, we know that length times the height. Now let's have a look at this. Length times height, that's the front, okay? Or the back, because they're the same, okay? They're the same shape, okay? Because the cross-sectional area is the same, right along the whole length if you were to slice that thing, okay, downwards like a loaf of bread. So, okay, that's the front and the back. There's two of them, so it's 2 times L times H, and we have L times W. This is the length and the width there, so that gets you the bottom, doesn't it? And also the top, because if you were to slice the same shape as you got there on that bottom face, all the way up there you get the same cross-sectional area, wouldn't you? Like slicing a piece of bread up that away, yeah? So L times W gets you the bottom, and it also gets the top, so there's 2 of them, 2 times L times W. And thirdly, we have the width times the height. That's the width, and that's the height. That's the right-hand side, isn't it? Okay, so the right-hand side and the left-hand side are both the same as each other, so there's 2 of those. 2 times W times H gets you the left and the right, okay? Now, please don't try and remember that formula. It's just a waste of time. You can get it from information you already know, okay? We're just working out all of the areas on the surface of that object, yeah? Now, let's do a cube now. A cube is a special case because all the sides, the lengths and the widths and the depths, if you like, or the lengths and the heights and the widths, as it is shown up here, they're all the same length. So therefore you've got 6 faces, yes, top, bottom, left, right, and also front and back, and that gets you 6 times L times L. Okay, so 6L squared. Yeah? Great. Now here comes a sphere. Surface area of a sphere is 4 pi r squared. That one you just have to remember. Okay, that's the outside surface of a spherical object, 4 pi r squared, where r is the radius. Now, cylinder. This one's pretty easy in terms of stuff you already know. This time we're dealing with a cylinder like, say, for example, a can of baked beans. Now, this is a closed can, so it's got a top and a bottom lid. Okay, now, this is a circle, that's a circle. Okay, so we've got pi r squared for there, pi r squared for there, the area of a circle, and 2 of them, that gets you 2 pi r squared. Right, that's this bit, right? Now let's deal with the curved surface here. Now, if you were to first of all get a can opener and take the top off and take the bottom off, you would just end up with this curved surface here. Now, if you were to slit that down there, like that, and then fold it out, you'd get this shape here, right? Now you've got to go back here and have a look. Well, this here, that length there, the perimeter of that circle becomes this length here, folded out. And you know that that perimeter of that circle, yes, is 2 pi r. So that's that length there, okay? And if it's got a height of h, that's that length there, and this whole thing folds out to be a rectangle, that curved surface does, yes? So therefore that area is 2 pi r times h, right? So therefore, there your total surface area of a closed cylinder is the 2 circles plus the curved bit up here, which becomes a rectangle when you fold it out, and therefore it's 2 pi r squared plus 2 pi r h and there she be. Yeah? Get it? Very easy. This is just a factorised version. I wouldn't try to remember it. I would just remember the formula for the area of a circle, the perimeter of a circle, and also the area of a rectangle. Okay, that's got that one done. Now let's do an example before we start forgetting some of this stuff. Okay, find the total surface area of the solids below. Correct to 1 decimal place. Remember, that's important. So this is, do you remember? 4 pi r squared. So 4 times pi times 7 squared, and then do it to 1 decimal place, and we get that, and therefore we get that, and look at that, 615.8 to 1 decimal place, square centimetres, because these dimensions are in centimetres. Okay, what about this one now? Okay, we'll do the surface area of this. So we've got 2 circles, top and bottom, and we've got this this curved bit here. So remember, 2 pi r squared, and then 2 pi r times h for the curved bit, right? So here it comes, closed cylinder, and the most important thing for you to remember is that you've got to get your units the same. See how this is really confusing? Look, ooh, danger, danger, danger. Centimetres, metres, no good, guys. You've got to watch for that and be on the alert, because they will try to get you. Yes, I know they're a bit nasty, but you have to be one step ahead of them, okay? 2 pi r squared plus 2 pi r h, yes. Okay, now do you just plug and play now, or plug and chug? So look, 2 pi times 50 squared plus 2 times pi times 50, that's the r, times 150 centimetres is the h, right? That's going to be a fairly big number. Woo, look at that. 62,831.9 square centimetres. Okay, so please be on the lookout for mixed units. Yes, that's the oldest trick in the book, and you have to be one step ahead of the action. Now this is cones now. Surface area of a cone, that's a very interesting one, isn't it? Now, the formula for the surface area of a closed cone, you've got this circular bit on the bottom. That's easy, that's just pi r squared, okay? But this bit here, this curved bit, this curved surface here is not quite so easy to see. So what I'm going to do now is just run you through it, so you'll then be able to know where it came from, because I think that's pretty important. In my book it's pretty important anyway. Now guys, have a look at this. If I was to take this, first of all to snip that, get rid of that circle, cut that out, I would just have like a thing looking like a party hat that you could put on your head when you have a birthday, wouldn't I? Yes? Now, if I was to get some scissors and cut that right down there like that, and then open it out, okay, just that curved bit there, you'd end up with a shape like this, okay, a shape like that. Now, remember, this is called S for the slanting side, okay, we'll call it S for the slanting or sloping side, and this equals this. And this thing here is actually just a sector of a circle. I know, shock horror. It's a sector of a circle. Now, what is the area of this sector of this circle? Well, there's this fantastic way of working it out. Now, let me just step you through it. Now, first of all, guys, what would the perimeter of a full circle with radius S be? In other words, what is the circumference of a circle of radius S? Well, guys, it's 2 pi S, isn't it? 2 pi S, yes? Okay? Alright, now that would be the full circumference, right around there like that. However, we've only got this bit of circumference here, right? And we know what this length is. We do know what this length is because it was this perimeter here opened out and folded out into this shape. So what is the length of the perimeter of this circle here, of the original cone? Come on, what's the circumference of a circle? Well, it's 2 pi r, isn't it? So this length here, folded out, is 2 pi r. Now, we can easily work out now what fraction this sector is of a full circle, because the fraction of a full circle that this thing is the same fraction that this perimeter is of the full circle's perimeter. Okay, so this perimeter, this bit of the circle here, this arc if you like, is 2 pi r from here, and if you divide that by the perimeter of a full circle, which would be 2 pi s, you get the fraction that this sector is of a full circle. 2 pi r divided by 2 pi s is the fraction that this sector is of a full circle, which is r over s when you cancel out the 2 pi's. So therefore, let's supply that fraction of a full circle of radius s. Now a full circle, the area of a full circle, of radius s. The area of a full circle here of radius s would be pi s squared, wouldn't it? Okay, so we say, alright, let's start with that and then just take the appropriate fraction of that to get the area of this sector. So pi s squared times this fraction, r over s, gets you this area. This area, okay, because the s cancels into that, you end up with pi rs. So that is the area. Pi rs is the area of this sector, okay. So now we've got it, guys, we've cracked the code. So therefore the total surface area of a closed cone, this beastie here, is the area of the circular base plus the area of the curved surface. We've just worked out the area of the curved surface is pi rs, and we knew that the area of the closed base was pi r squared, so just add them up and you've got it. Okay, so I recommend you remember this one, pi r s, for the curved surface. Don't bother remembering that, you already know that. That's the area of a circle. Okay, there you go, there's your area of a closed cone. If they give you an open cone, it's just pi rs. If they give you a closed cone, it's pi r squared plus pi rs. Alright, very good, let's do an example. Find the total surface area of the cone shown. Well, my goodness. Now the first thing, are the units consistent? Yes, yes. So we're in square centimetres, everything's good. We don't have to head off a booby trap here with mixed units. Alright, so let's just plug and chug. Here it comes. The area of a circular base plus the area of the sloping cone part would be pi r squared plus pi r s, where s is 15 centimetres in this case, and we just plug it in, and what do we get? I did it to one decimal place for you, 1017.9 square centimetres. Alright, very good. Now, what's this? This is just a statement that the total surface area of composite solids, that's basically solids that you know the shape of, joined together into what's called composite shapes. So how do you do that? How do you work out the total surface area of composite shapes? You basically just sum up the areas of the solids' faces, okay, the faces of the solids which you know the formulas of, okay. Now this is important, when two smaller solids are joined, the surfaces involved in the join will no longer be part of the surface of the composite solid. For example, if you had a square-based pyramid, okay, a square-based pyramid, and it's stacked on top of a cube of the same base dimensions, then you've got to think about that, okay? The two faces in the join, that is the cube's face and the pyramid's base, which join to each other, are therefore inside their internal sides, okay, of the new shape, and therefore they're not part of the outside surface of the solid. Do you understand? Yes, yes, and let's do an example. Okay, find the total surface area of the object shown. Now look, guys, do you recognise what to do? Well, we've got a cube here of dimensions 10 by 10 by 10, and sitting on top of that cube there's a pyramid here, right, a square-based pyramid, and it looks like it's got a side length here of 10 and there of 10, and a sloping side here of 6 centimetres, okay? So, for each of those triangular faces, let's draw those in 2 dimensions first, right? That's very important. Otherwise you can get yourself very tangled up. Now what I've done here, to work out the area of a triangle, I'm going for base times height over 2, perpendicular height. Now I'm looking front on, I've got a base of 10, I've got sloping side lengths of 6 here and 6 there. So can I work out h? Because if I can say base times height over 2. And how would you work out h? Yes, you would use Pythagoras' theorem, wouldn't you? So, what do? We say, okay, h squared is equal to the hypotenuse squared, or 6 squared, minus this length here, which is going to be 5 squared. So I'm dealing with this right angle triangle here. See, h squared is hypotenuse squared minus this length here. Half the 10 is 5. So 6 squared minus 5 squared, what does that come to? It comes to 36 minus 25, which comes to 11. Therefore, h would be root 11. Okay? So therefore, look, we've got it. We've nailed it, guys. You see? So the area of the triangle is a half of 10 times root 11. And that's just one of them. But how many are there? Yes. So we've got 4 of them. And we have nailed it, right? So now just make sure I'm right. 4 times a half is 2. 2 times 10 is 20. 20 root 11. Okay, that is the surface area of the 4 triangular faces of that pyramid sitting on top of the cube. Alright? Now we're not going to do the base, because the base is now an internal surface of this object here, right? We want the outside surfaces, alright? So all we've got to do now is do the cube. So we want, how many faces are there on that cube which are outside, external surfaces? Yeah, we've got 5 of them, right? We've got the 4 sides and the base of the cube, right? Not 6, but 5, okay? 5 by 10 by 10 gets us 500 square centimetres, and the final knockout punch, guys, is the total surface area of the pyramid bit, and the cube bit is that plus that, and we might as well do it to 1 decimal place. It comes to 566.3 square centimetres, yeah? Ain't it grand? Now, here's our final question. My goodness. We've got a silo, okay? Something they put wheat in, yes? Or something else in. So the silo shown at right is to be built from metal. The top portion of the silo is a cylinder, that's this bit here, of diameter 4 metres and height 8 metres. So let's just step that out, 4 metres there, 8 metres there, yeah? Good. The bottom part of the silo is a cone, okay, composite solid, of slant height 3 metres, yes, yes. The silo has a circular opening of radius 30 centimetres on the top. Okay, that must be there. Right, now look, warning, 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 mixed units. You switched on to the mixed units, you need to be. Okay, now what do they want to know? What area of metal, that's e.g. What total surface area, to the nearest square metre, right, is required to build the silo. That's part A. And if it costs $12.50 for every square metre to cover the surface with an anti-rust material, how much will it cost to cover the silo completely? Piece of cake, guys. Piece of cake. Let's do A and not get too bound up about part B yet. Okay, so A, we've got to do a composite solid here, right? Oh, look at that. I've got them all labelled for you. So I'm doing the circle here. I recommend you use the same technique. It's really, really good in my experience. A circle there, okay, with a bit of a hole in it. That's the 30 centimetre thingy they were talking about there. Radius 30 centimetres at the top. That's the circle there, or the donut if you like. Then we've got this curved bit here, number 2, and then we've got a sloping sided cone here, and this of course we don't do, this base of the cone, because there ain't no base, it's all inside, it's just space in there, right? Yes, that's internal, that surface, or it's not even there actually. Alright, let's go for it, guys. What's the area 1? Right, now, how do you do area 1? Well, now the first thing to do is you've got to be very careful here, because we've got to do area of a circle, the outside circle minus the area of the little circle in here gets you the area of the donut. But you've got to convert that 30 centimetres into metres, right? Now, be careful. This is 2 meters radius, right? 2 meters, not 4. Right? So pi 2 squared minus pi times 0.3. 30 centimeters is 0.3 of a meter squared, right? So we're in square meters, guys, and we haven't fallen for the trap of the mixed units. So just multiplying that out, you get that, and then you will get that. Now, area 2, that's the curved bit of this cylindrical part. Now it's just going to be 2 pi RH from our formula earlier. 2 pi, where R is 2, H is 8. Yes? Very good. 32 pi, 2 8 to 16 times 2 is 32. 32 pi square meters, very good. Area 3, we're on the home run now, guys. Area 3 is just pi RS, right? Pi RS, where S is the sloping side, which is 3. Okay, and R is 2, so it's 6 pi square meters, and we're nearly there. We've just got to add up area 1, 2, and 3, which will fill us with glee. There it goes. Now, I've done it there for you, and that comes to 41.91 times pi square meters, right? And that, now I'll work that out, it comes to 131.664, so it's 132 square meters to the nearest square meter, because that's basically what they asked us for in this question. Make sure you read the question before you leave it, right? Now, how do you work out part B? Think about this. Let's use some round numbers. If it cost me $10 for every square meter to cover 100 square meters, how much would that cost? Well, there are 100 square meters. It's costing me $10 for every one. So wouldn't you multiply the number of square meters by the cost for every one of those square meters? I think so. So we do the same thing here in part B. So the cost is $12.50 for every square meter times the number of square meters, which is 1,650. So there's your answer, guys. There's your answer. Hope you enjoyed it, and you go and do some practice now and have some fun, and we'll see you next time. All the best.